In this video we are going to discuss about the CMOS transistor theory. So here on the completion of this topic, the students will be able to describe the equation for source to drain current in the three regions of operation of a MOS transistor, and they can able to draw the VI characteristics of MOS transistor. So here we will be discussing about two things. One is nMOS saturation IV characteristics and PMOS IV saturation characteristics. So in the case of nMOS IV characteristics, this transistor is nothing but a three terminal device. So there is no single IV characteristics. See here, if you note it, that is the gate transistor will be equal to constant value. So that is, if VGD value, that is drain gate voltage, is less than the threshold voltage, this channel pinch off near the drain. So when this drain source voltage is greater than the saturation voltage, that will be equal to the VGS minus VT. So here we can typically find that the gate insulator value, that is IGS, is equal to constant value, and also we define this MOS IV transistor as IDVS VDS for a fixed value of the gate source voltage. And here we can see this operates in three modes of operation. So here we will be studying about the cutoff mode, saturation mode and the linear mode. So here this region occurs in three types of characteristics. One is triode mode, one is saturation mode and cutoff mode. So as usual, we know this cutoff mode occurs when this value, that is gate source voltage, is less than the threshold voltage. So we say that value, that is ID value, will be equal to 0. And the triode mode, what it occurs means when this gate source voltage is greater than the threshold voltage and this drain source voltage is very less than the gate source voltage minus the threshold voltage, this ID is equal to W by L mu and Cn Ox into VGS minus VTH minus VDS by 2 into VDS. And when in the saturation mode, we can say that this VGS is greater than the VTIN, or VDS is greater than the VGS minus VTH. So now this drain source voltage, when we see, there is no longer increase in the current. So we write this equation as IDS is equal to beta into VGS minus VT minus VD sat divided by 2 into VD sat. So here when this VGD value is very less than the VT, this pinch off near the drain. So when this VDS is greater than the VD sat, we write this equation as this VGS value will be minus the threshold value. So we can write the final equation as beta by 2 into VGS minus VT the whole square. So as I said, there are two modes: cutoff region, linear region and saturation region. So the three conditions satisfies. When IDS value equal to 0, it is nothing but cutoff region, and when IDS is equal to beta into VGS minus VT minus VDS by 2 into VDS, it is linear region. Beta by 2 into VGS minus VT, the square, is nothing but the saturation region. So that when there is a high voltage, that is drain source current is high, it occurs in the saturation region. So here we are seeing the 6%, there you can see an example, that is 0.6 mu process for this one. So from this we are taking AMI semiconductor, TOX is equal to 100 amps. So this value is equal to, that is, we know that IDS and VDS we are plotting. So here we will be finding out the linear region, cutoff region and triode region, or we can say cutoff, linear region and saturation region. So while using this value, that is W by L value in the equation, that is beta is equal to mu into COX into W by L, I am substituting the value, we get 120 W by L into mu A by V square. And the next one is PMOS IV characteristics. So this PMOS IV characteristics is, the difference is the symbol will be having a dot at the gate. So here in the PMOS we have a dot at the gate, and nMOS we don't have it. So ID, VGS, VDS and this threshold voltage, these are negative for PMOS. So these values are positive for nMOS. So when the channel is formed here, when VGS is less than the threshold voltage, it is opposite for nMOS. Saturation occurs means also VDS is less than the VGS minus VTP, means then it is opposite of the PMOS, that is nMOS. nMOS and PMOS are opposite. So while we see this one, this doping's voltages will be the inverted position of nMOS. So here this mobility are mainly determined by the holes, and next this has the typically it has 2 to 3 lower than the electrons, and also the wider to the provide the same current. So here we can see this occurs in 3 modes. So in this 3 modes we can assume the source to be in ground. So this in this cutoff region we can see the VGS will be greater than VTH, and then the triode region, that is VGS is less than VTH, saturation region VGS is less than VTH, and VDS is less than VGS minus VTH. So you can see the example as if the source is greater than 0, that is pass transistor is passing as BDD. So here if VG is equal to VDD, then if Vs is greater than VDD minus VT and VG is less than VT, this transistor could turn itself off. So this nMOS pass transistor pull the higher value, that is VDD minus VTN, which is degraded as 1. So the degraded value will be slowly decreasing, and this pass transistor is having the lower value. So here in this value, when lambda is 0, or if you are currenting the constant value of current, it occurs in the saturation mode. So this pass transistor circuits, you can see the value as 0 or 1. So when we transfer a high current, or if you are transmitting a higher value, then or VDD is equal to 1, it operates in the PMOS, and if it is a 0, then it operates in the nMOS modes. So it has an effective resistance. So it is not relatively enough for the modern transistors, and also it has some limitation, that is it is too complicated for the hand analysis. And the simple thing is it can treat the transistor as resistor, and also we can replace with the effective resistance, and it is too inaccurate to predict the current at a given time. Next one is RC delay model. So in this RC delay model, you can see an equivalent circuit for the MOS transistor. So this contains the ideal switch, capacitance and on resistance, unit PMOS and unit nMOS. In the case of unit PMOS, you can see the 2R resistance when compared to the nMOS, and the capacitance will be seen for both PMOS and nMOS, but comparatively nMOS and PMOS are the resistive value 2 times greater than the nMOS. So this capacitance proportional will be the capacitance is proportional to the width, and the resistance is inversely proportional to the width. So you can see the block diagram here, and the resistance and the capacitance value is here. So the unit transistor value is minimum, and it has a minimum width. So the width is compared, both the things are compared. nMOS is equal to 2 times of the resistance of PMOS. And this inverter delay estimate, while we are estimating the delay of this fan out of one inverter, if you are taking for nMOS 1 means surely the PMOS resistance value will be 2. So that is given here. And if you are calculating the value of this one, first we will be replacing this transistor as a resistor as well as a switch. So that is given here. So each one will be having a capacitance, and finally we are finding out the value of the inverter. Estimate delay. So delay is nothing but 6 RC. Quiz questions on the CMOS transmitter delay is: first one, draw the transfer characteristics of CMOS inverter and implement the RC delay model of MOS transistor. Thank you.